Hello and welcome back. So today we are going to look at entropy in a little bit more of detail. We have already looked at how to calculate entropy differences in the case of various processes. We have looked at the definition of entropy. We have looked at the Clausius inequality and so on. But there are a few more aspects of it which we will look at today. So the principle of increase of entropy is something which we very briefly touched upon. So we said that if you have an isolated system, then the entropy of such a system cannot decrease, so it can either remain constant or it can increase. What we see is that for an isolated system, by definition, there cannot be any mass transfer. Since it is isolated, it means that it's a closed system and it is insulated. Therefore, there cannot also be any heat transfer. It has no interactions with the surroundings. And therefore, what we see is that if there are any irreversibilities within the system, the entropy of the system must increase, and at best the entropy can remain constant. So therefore it can either remain constant or it can increase, but it cannot decrease. So we can try to see how we get this concept, and over here shown we have a system whose temperature is at T. Let's say it has some interaction with some surroundings which are at some temperature T0. And because of this interaction, there is some heat transfer between the surroundings to the system. So the way in which it is shown here, the transfer of heat is from the surroundings at T0 to the system at T, which means that T0 must be greater than T for spontaneous heat transfer to occur. The amount of heat which is transferred is shown as del Q, and the system may do some amount of work, del W, on remaining parts of the surroundings. We know that ds is greater than or equal to del Q by T. We have proved this before. We said that for a reversible process, ds is equal to del Q by T. For an irreversible process, ds is greater than del Q by T. So in general, we can write it in this form. We are of course only looking at processes and not for a cycle, because we know that for a cycle, when a system undergoes a cycle, the change in any property must be zero. So entropy being a property, the change in entropy would also be zero for a system undergoing a cycle. But if we take any process, then we can write this in this form. And we also know that from the first law, if we have the surroundings giving an amount of del Q of heat to the system, then we can write the interaction of heat for the surroundings and interaction of heat for the system, and they must be the same. So we know that del Q for the system, numerically, that is, if we take the magnitude of the value, that should be equal to del Q for the surroundings, and we can call both of these as some del Q in general. We are of course only looking at the magnitude here. We have not taken the direction into account. So ds for the system should be greater than or equal to del Q by T. That is from the Clausius inequality and the definition of entropy. Similarly, ds for the surroundings should be related to del Q by T of the surroundings. So what we can assume is that the heat transfer is isothermal for the surroundings. So we can assume that the temperatures of surroundings does not change because the surroundings are very large, and therefore the heat transfer can be assumed to be reversible for the surroundings. And if it is reversible, what we know is that we can use the equality sign instead of the inequality, and ds from this expression would be greater than or equal to some del Q by T. Now remember, our convention is that when the system, whatever we take as the part under consideration, when something gives out heat, the heat convention is negative, and when something receives heat, the convention is that it is positive. So for the system, which is shown in blue over here, it is receiving heat, so del Q is positive and the temperature at which it is receiving is T. So we have ds for the system which is greater than or equal to del Q by T. For the surroundings, it is giving out an amount of heat as del Q. So therefore by our convention, this del Q should have minus sign. It is a negative del Q. And the temperature at which it is giving heat is T0. So we see that ds for the surroundings is equal to minus del Q by T0. Now if we want to find out the net change in entropy, we can sum up the changes in entropy of the system and the surroundings, which is what we are doing here. So ds net is the net change in entropy, is the change in entropy of the system plus the change in entropy of the surroundings. And what we can do is we have expressions for each of these over here. We can substitute them. Of course, I could have written this as capital S also because I'm using capital Q here, but this would that is possibly the more appropriate way, but it is showing up here as the small alphabet. So we have the total change in entropy, the net change is del Q by T for the system, which is this, minus plus of minus del Q by T naught, which is the value for the surroundings. So what we see is del Q is the same here, so we can take it out common, and then what we get is it is del Q into 1 by T minus 1 by T naught. What we have seen here is we have considered a condition where the surroundings are a temperature of T naught, which is greater than the temperature of the system. So T naught is greater than T, therefore 1 by T naught must be less than 1 by T, therefore this quantity must be positive. The quantity within this brackets here must be positive. We've already seen that del Q is positive because del Q is what is coming into the system. So this is positive and this is positive, therefore ds net is some quantity which is greater than or equal to 0. If the temperature of the surroundings and the systems were the same, then 1 by T and 1 by T naught would be the same, which would be the case when you have isothermal heat transfer from the surroundings to the system. In that case, what we see is that we can have reversible heat transfer because then ds would be equal to 0. But the moment we have a difference in temperature between the system and the surroundings, we see that ds net is greater than or equal to 0, which means that when we have temperature gradients of this kind and we have heat transfer over a temperature gradient, a finite temperature gradient, it increases the entropy of the universe, and we see that ds net is greater than or equal to 0. What we can also see is that if, for example, we considered T naught to be lower in temperature than T, then what would happen is that heat transfer would be in the opposite direction from the system to the surroundings. Supposing T was greater than T naught, heat transfer would go up in this way. Then what we would see is 1 by T would be less than 1 by T naught. This term would be negative. But then del Q is also going out of the system, so del Q also would be negative. And then we see that ds net in that case also is going to be greater than or equal to 0. So what we see is, irrespective of whether the system is transferring heat out to the surroundings or the surroundings are transferring heat to the system, as long as the temperature of the system and the surroundings are different, we see that there is a net change in entropy of the system and the surroundings put together, or essentially there is a net change in entropy of the universe, which is essentially our principle of increase of entropy. So whatever is the change in entropy is what we call as the entropy generation, and we see that that value is equal to del Q into 1 by T minus 1 by T naught. So this is the amount of entropy which is generated when we have heat transfer across a finite temperature difference. So what we see is that unlike energy, which is conserved, entropy is not conserved, and entropy is actually generated when you have this kind of process taking place. We had said earlier that ds is greater than or equal to del Q by T. We got this from the definition of entropy and Clausius's inequality. But this is an inequality, so it's not always very convenient way to write. So what we often do is to write it in this form as ds is equal to del Q by T, which is the value it would be if it was a reversible process. So this del Q is for a reversible process. And we can add ds gen, which is the value which gets generated if you have an irreversible process. So what we see from here is that if the process was reversible, this term would be 0 and ds would be equal to del Q by T. If the process is irreversible, this term will be greater than 0, it will be positive, this term cannot be negative, and we see that ds would be greater than del Q by T because it will be del Q by T plus some amount which is there. And del Q can have either a plus sign or a negative sign depending on what is the direction of heat transfer. We see the temperature cannot be negative because it's absolute temperature. If you have heat lost, then del Q is negative. And what this expression here shows is that even if you have heat lost, you have heat generated. And if you have heat which is being transferred to the system, then this is positive and this still remains positive. So the change in entropy is greater in both the cases. Whether you have heat loss or heat transfer to the system, you have dsgen, which is positive in both cases. So the previous example was in some sense about heat transfer through a finite temperature difference, but we can see that a little more in detail over here. Over here we have a source which is shown in red on top, which is at some temperature of TH at some high temperature. We have some sink which is at some temperature TL, which is lower in temperature. So there are two ways in which you can transfer heat from this to this. The first way is what is shown here. You have an engine, a Carnot engine, a reversible engine. You take heat from this high temperature source, run the Carnot engine, do work on the surroundings, and then reject heat to this low temperature reservoir. So whatever is the amount of heat coming here is essentially what is transferred in net from there to here. That is one way in which you can transfer heat. And this process, as we have discussed earlier, is reversible because we have over here a Carnot engine, which is a reversible engine. Now, I had transferred some heat from there to here. If I want to remove this heat back from here, all I now need to do is to reverse the direction of this engine. Since this is a Carnot engine, we know that it is a reversible engine, which means I can run it in reverse and it acts as a heat pump or a refrigerator. So whatever is the amount of work it produced over here when transferring heat from there to here, the same amount of work I can now give, and it can transfer the same amount of heat back from TL and send it back to this TH. So what we see is, in this case, I can actually have heat transferred in either direction. So I can have heat transferred from TH to TL, and it does work on the surroundings, or the surroundings do work the same amount of work, and now I can transfer heat back from this low temperature to this high temperature, and nothing has changed with the universe. So this is a fully reversible process, and we discussed that if a process is reversible, it must be both internally and externally reversible. So this is both internally and externally reversible, and in this process I can transfer heat in either direction, either from high temperature to low temperature or low temperature to high temperature. So this is the way in which we can transfer heat reversibly. But there is the other way, which is in some sense what we see more commonly, where we have heat transferred from a high temperature reservoir to a low temperature reservoir by bringing them in contact. So here what we see is, in this direction, from the high temperature to the low temperature, heat gets transferred spontaneously. We don't need to do anything for this transfer to take place. But if we now transfer heat like this, and we want to now transfer the heat back from here to here, what we see is the only way we can do it is now by running a heat pump or a refrigerator. In order to transfer out heat from this low temperature to this high temperature, we need to now run either a heat pump or a refrigerator. And if we want to run this, it means we have to do work. So what we see is, in this process over here, there was no work involved. The heat got transferred spontaneously. But if I want to do the reverse process, I need to give work, which means the energy of the surroundings is coming down because it has to do work now to transfer heat from here to here. So in one direction, this happens spontaneously. In the other direction, the surroundings suddenly come into play because they need to do work. And therefore we see that this process is irreversible. Because if I want to do it in this direction, I can do it easily. If I do it in this direction, the surroundings change. So at the end of this entire process, the surroundings and the system are not exactly where they were because the surroundings have changed. In this case, whatever was given out to the surroundings is taken back. The surroundings are the same. We get back the same amount of energy in both these reservoirs. But in this case, what we see is we can get back the same amount of energy, but the surroundings have changed. Therefore, what we see is that this is no longer a reversible way of transferring heat. So, when we have heat transfer through a finite temperature difference, we see that it causes irreversibilities.